Hello everyone, I'm Parisa Borhani-Darian, and today I want to talk about the deep neural network approach to detect GNSS spoofing attack. In the introduction section, I will talk about very briefly about the sensitivity and vulnerability of the GNSS, and then talk about the objective and novelty of the paper, which is the exploring the capability of DNN deep neural network to detect GNSS signal spoofing attack. In the core section, I will talk about signal and spoof signal model, and then talk about deep neural network application, DNN structure, and DNN parameters. And then I will talk about the simulation result as well as the conclusion. GNSS receivers are very sensitive and vulnerable to deliberate interference, which opens the door for attackers. Attacks on GNSS receiver might act at two different categories: physical attacks on the receiver, which is non-signal attacks, and attacks at the GNSS signal in a space level, which is the signal attack. The signal attack is the intentional attacks on GNSS signal, which has three different forms: jamming, meaconing, and spoofing. In this work, we are focusing on the spoofing attack, which is the transmission of forged GNSS-like signals with the intention of producing a false position estimate and eventually take control over the receiver. The objective of this paper is exploring the capability of deep neural network model to detect GNSS signal spoofing attack. The novelty of the paper is using deep learning model for signal detection process in presence of the spoofer. As we can see in the figure below, we will have two types of GNSS signal model. That the left figure shows the spoofer-free GNSS, and the right figure shows the spoofed GNSS signal. So these two types of signal will feed to the deep neural network, and we expect the neural network to detect the spoofer attack. In the GNSS spoofer detection, acquisition is the first stage in the operation of a GNSS receiver. So for this paper, we are evaluating the cross ambiguity function, which is the correlation between the received signal and the local pseudocode. When the signal is present, the cross ambiguity function exhibits a large peak. And also, we are considering two different hypotheses: null hypothesis H0 and alternative hypothesis H1. In the null hypothesis, the GNSS receiver will have the legitimate signal plus noise. But in the alternative hypothesis, which is H1, the GNSS receiver will have legitimate signal, spoof signal, and noise. That you can see in the figures below, that the left figure shows the null hypothesis, that we just have the legitimate signal plus noise, and the alternative hypothesis, which is the right image, shows the legitimate signal, spoof signal, and noise. The signal model is the signal that the receiver receives from N satellite plus noise, where the legitimate signal calculate from this equation, which is where the alpha is the carrier amplitude of the received signal, B is the signal data bit stream, C is the spreading code of the satellite, omega C is the carrier frequency, omega IF is the intermediate frequency, and tau I is the signal code phase, and phi is the carrier phase. So now, what is the spoof signal model? The total signal at the victim receiver antenna during the spoofing attack is calculating from this equation, that it has the legitimate signal, spoof signal, and the noise. The spoof signal will be considering as this equation, and also the spoof signal must be very similar to the true signal. So most parameters of the spoof signal are the same as the true signal, such as data bit stream, spreading code, intermediate frequency, carrier frequency, These are the same with the true signal, except those parameters that affect the position estimation that cause to deceive the GNSS receiver, such as the number of the spoofing signal, the amplitude of the spoof, the code phase of the signal, and the carrier phase of the signal. So let's talk about a deep neural network model. Deep neural network composed of neurons that are the information processing unit for complex data processing. The neural network consists of input layer, 2 or more hidden layer, predefined activation function that connect adjacent layer, and output layer. One of the most important aspects of the neural networks model is how to design and choose a network to get the high accuracy and the less network complexity. In this work, we are working on 2 different neural network structures: multi-layer perceptron, which is MLP, and convolution neural networks, CNN. The first neural network structure that used in this work is multi-layer perceptron network. That is the traditional neural network with the moderate complexity. As you can see, this network consists of several fully connected layers. And at the input layer, we have the data set, which are considered the cross ambiguity function as the data set, and define the 2 hypotheses, H0 and H1, as the ground truth. And we fed this data set to the network. The network used the ReLU activation function and consider dropout with probability of 50%, which are these black circles in the layers that ignored some random neurons in the hidden layer. At the last layer, we have 2 neurons, that the number of the neurons in the last layer depends on the number of the class that wants to classify, which provide the probability of each class. That helps the network to detect the input belong to which class. And also we use the softmax layer for classification in the last layer. The second network that we are using is the convolution neural network. The input layer and the output layer of this network is the same as the multi-layer perceptron. However, these networks are most popular model to learning the class label from the dataset. Each layer has the filter that learn to identify different features from the dataset. At each layer, filters are applied to each training dataset, and the output of each convolution layer will be input of the next convolution layer. This figure shows, the below figure, this figure shows how the filter works in the dataset. The filter strip the input image from left to right and top to down by using the stride. Here is the stride is 2 that shows the number of the pixel that each time the filter shift. So at the first time, filter size is 3 by 3. It select 3 by 3 pixel and pick the one feature of that selected pixel as a 1 pixel. And then it's shifted by a stride 2 to the left, to the right. And when it reached the end point, so it comes down by a stride 2 and then again go to the right, which is the last one, is the purple. The convolution neural network consists of n convolution layer, which is followed by n fully connected layer. And it used the ReLU activation function, used batch normalization layer, and used softmax layer for the classification. This table shows the different network structure that we use in this work, which are MLP, simple CNN, and complex CNN, which is the same as VGG16. The training and test dataset are the same for all three networks. The training dataset is 8500 for all three, and the test dataset is 1500 for all three. The number of the layer in MLP is 8 fully connected layer. For simple CNN is 3 convolution layer and 3 fully connected layer. And for the complex CNN, it's 13 convolution layer and 3 fully connected layer. I use the SGDM and ADAM optimizer for all three networks as an optimizer. And the learning rate, activation function, and number of the epoch are the same for all three networks. Also, all three networks use the dropout on their fully connected layer. This figure shows the training accuracy of the three networks with ADAM and SGDM optimizer for CN0 between 33 to 45 with two different NNCI, number of non-coherent integration, 10 and 20. As you can see in the figure, the dark blue bar shows the complex CNN with ADAM optimizer, and the brown bar shows the complex CNN with the SGDM optimizer. As you can see here, for both different NNCI, the complex CNN outperformed the simple CNN and the MLP. And also, those networks that use the ADAM as the optimizer has the better accuracy, better training accuracy in compared with the SGDM optimizer. So for the rest result, we are using, I use the ADAM as an optimizer. And also what we can conclude here that by increasing the number of non-coherent integration, the training accuracy will be increased. These figures shows the ROC curve result under number of non-coherent integration of 10. That you can see the left figure is the simple CNN and the right figure shows the MLP. The simple CNN outperformed the MLP. That you can see here that probability of detection are higher than the probability of detection in the MLP. Both networks hardly attain the theoretical ROC even in the higher number of the C over N0. And as you can see here, for the simple CNN, for the C over N0 43 dBHz and above, it reached the theoretical, but this is not happened for the MLP. In the previous slide, we conclude that simple CNN outperformed the MLP. These slides I'm comparing the complex CNN with the simple CNN. As it is obvious in the figure, the complex CNN outperformed the simple CNN. That, as you can see, for the C over N0 equals 35 and above, it reached the higher probability of detection than the simple CNN. And also, when the C over N0 value is equals to 37 dBHz and above, the deep neural network result attain the theoretical ROC. Here, this figure shows the probabilities against the threshold under NNCI 10. As you can see in the left figure that shows the probability of detection versus the threshold, all value of the C over N0 reach the convergence point at the point when the threshold is equals to 0.5. And this is the same for probability of false alarm for all C over N0. So all C over N0 reach the convergence at the point of the 0.5. So we consider the threshold 0.5 as a convergence point. Here it shows, this figure shows the network evaluation for different C over N0 under NNCI is equals to 10. As we expected, the complex CNN outperformed the simple CNN and the MLP. The left figure shows the probability of detection. That we can see that the complex CNN has the better probability of detection in compared with two others networks. And for the probability of false alarm, which is the right figure, the complex CNN has the lower probability of false alarm for higher C over N naught, but in some value of the C over N naught, the probability of false alarm of the complex CNN is not good as we expected. So we decided to test the complex CNN with different number of non-coherent integration. So we test the probability of detection and probability of false alarm with the different number of non-coherent integration, which are 10, 20, 30, and 50, which are purple to blue respectively. As it is obvious here, when the number of the non-coherent integration increase, the probability of detection increase too. So as we can see here, for the blue one, we will have the high probability of detection even for the lower C over N naught, which is not the same for others NNCI. And also for the blue one here, that is the right figure shows the probability of false alarm, that we can see that the blue one reached the probability of false alarm equals to the 0. So we can conclude that when the NNCI is equals to 50, we can get the probability of detection above 90%, and the probability of false alarm close to the 0. This figure shows the histogram under H0 and H1 for C over N naught equals to 45. The left figure shows the complex CNN, and the right figure shows the simple CNN. What we expected from the histogram plot, that when the histogram has the less overlap, we will have the better probability of detection, that it's happened for the complex CNN, not for the simple CNN or the MLP. So as we concluded, the complex CNN has the better probability of detection than the MLP and simple CNN, which we can see the result here in the histogram plots too. We can conclude this paper that we present training and testing result of a spoofing detection method that leverage deep learning model. A data-driven approach is presented that learns the changes in the cross ambiguity function when one or multiple spoofers are present in addition to the legitimate signal. The probabilistic detector compares the posterior probability of each hypothesis to make a decision, therefore providing a quantified uncertainty on the decision. Result shows that more complex CNN provide better probability of detection and probability of false alarm performance. And the complex CNN outperforms simple CNN, and simple CNN perform slightly better than the MLP. Increasing the number of the non-coherent integration increase the probability of detection and decrease the probability of false alarm, therefore improving the detection capability of the method. Thank you. I hope that you enjoyed the presentation, and I will be glad to hear your comments and answer your questions.